In general, one of the things I find that happens at Hopkins is people, because our registration system is so inefficient, people have a tendency to register for classes that they are then going to drop. And they know they're going to drop, and that just happens. And then sometimes people get freaked out because like they see there's too much coding or whatever, and then they drop as a result of that. So I'm going to do my best to make some of that latter thing happen. I can't control the former thing. What I would suggest, a bunch of people are inevitably going to come up to me after this class and say, you know, I want to be in this class. I would strongly, in fact, I'm going to ask you all to hold that until the end of next class, which I believe is next Wednesday. And so that, I'm praying, will give the folks who are definitely going to drop a chance to drop. It will give the folks who are scared off a chance to be scared off. And then we can address this on Wednesday. My general attitude towards this is if you have it in you, if you have the moxie to show up twice to this class, I would, under ordinary circumstances, let you all in. However, as you can see, we have some physical constraints in this room, and I don't want this to be like a really unpleasant experience for everybody. Last semester, I had to teach a class in an auditorium, and I resolved never again to do that. It was like the worst feeling ever. Nobody would participate. It was awful. So unfortunately, Hopkins will not give me probably a bigger room that isn't an auditorium, and I'm just not going to do that. So anyway, what the end result of this is, come back on Wednesday. If we get through today and you like it, come back on Wednesday and we'll see where we are. Okay, good. So until I have slides, I'm going to have to kind of improvise here for you guys. Or just use my slides, even better. Okay, good. So this is Practical Cryptographic Systems. If you guys are not planning to be in Practical Cryptographic Systems, this would be a good time to leave. Before I get there, I should probably introduce myself. My name is Matthew Green. I'm a professor in the Computer Science Department. I also work in the Information Security Institute. Give you a 30-second background of what I do. Once upon a time, I worked for AT&T Labs as a technical staff member. I decided to get my PhD, started a company, ran the company for a while doing consulting work for kind of Fortune 100 companies doing security consulting specifically. Decided I hated running a company and I wanted to be back in academia. So I came back as a professor, and since then I've been doing research in a lot of different areas. I still do some kind of outside consulting. So I've had a really good career in the sense that I've gotten to touch a lot of actual systems, security systems, cryptographic systems, and see that they're all kind of held together with baling tape, which happens. And I've also had the opportunity to kind of see things from the research side, which I think is much more interesting, but also it tends to be a little disconnected from the real world. So I like having the ability to bridge what industry is doing and what we're doing here. And so that is kind of the inspiration for this class and what we'll be talking about for the next 9 or 10 weeks. All right, so first off, I want to give a quick intro to this course and what it's all about. Okay, so this is a class, obviously the name is Practical Cryptographic Systems. That implies a couple of things. Okay, so the first question is, what is a cryptographic system? Obviously, it is a security system. It's a security system that happens to use cryptography. That's it. Now, many systems use crypto, and they're all cryptographic systems. We'll be focusing to a large extent on systems that really fundamentally rely on crypto, which still covers a huge, huge percentage of the world. The interesting thing about these cryptographic systems is they are astonishingly easy to screw up. And that goes above and beyond what is the case in ordinary security systems, which are already very easy to screw up just because people make mistakes in software. Once you start including cryptography into things, people really, really, really get it wrong. And I'm going to talk about a lot of that. In fact, one of the focuses of this class is looking at those mistakes people have made and trying to understand, motivate us to do things better. Okay, all right, so to give you a few examples of things that people have done very poorly, I wonder if anyone can, this is probably the most famous, at least security exploit. Go for it. Good, Heartbleed. Who can give me a less than a minute summary of what Heartbleed did?
So you basically, you say, hey, server, are you there? And then the server's like, okay, I'm here. Okay, great, I have a word. And you say, it's this many letters. Give me the word back and then I'll be okay.
Good.
And so you say, I want the word green, and it has 5 trillion letters, and then you get everyone's private data.
Good, okay, fantastic. So interestingly enough, Heartbleed was actually kind of a traditional software flaw, but what made it interesting from a cryptographic perspective was that it was a software flaw in a very important library, which was OpenSSL. Great, and what's important about OpenSSL is that it provides, maybe with a little bit of exaggeration, but it provides the security for a huge percentage of the internet. Not only that, but it sits at a very low level in the stack, and it's enormously complex. If you think about the network stack, you've got like your IP, your TCP stuff, and even in relatively new operating systems, there's still, these are well-studied chunks of relatively simple code. OpenSSL was not. OpenSSL was like the difference between Rhode Island and Texas in terms of, it was the Texas, not the Rhode Island. When you compare it to things like, simple TCP stacks, and it was not very well maintained, so there were bugs in it. And the problem with those bugs is that when somebody finds a way to exploit one of them, a lot of important data gets potentially stolen. But there have been other very serious attacks which were not maybe exploited quite as much in the wild because they were found by technical experts and fixed before they could be exploited. One of them that came out maybe a year or two ago was the Drown attack. There have been a handful of these. Drown was a flaw in the TLS protocol, which is the same protocol that OpenSSL implements, that allowed people to basically just strip the cryptography off of supposedly encrypted connections. But there have been so many of these, it's kind of hard to give a list. Bluetooth is a mess. GSM encryption, which is to say the protocol that drives your smartphones, at least when they make calls and send data, tons and tons of flaws, and so on, credit cards, etc. Pretty much every security system, if you poke it at some point in its life cycle, you will find bugs falling out of it. Okay? And so when these things happen, when these bugs come up, there are some, some interesting things that happen. So way back in 2003, we had a guy who found bugs in DVD players that allowed you to play discs that were supposedly protected, and he was actually prosecuted. You have headlines like this. So when these systems break down, it kind of matters for the world. Okay. So I've said this already, but the motivation for this class is that building successful systems is going to require a lot more than you would get from just a plain crypto class. You need to know some crypto, and that is what we're going to cover in the first half of this class. It's really cross-disciplinary. We have to know crypto. We have to know just general security knowledge, things that you would probably otherwise get in the introduction to computer security and privacy. We have to know a lot about software engineering, because fundamentally this is all software engineering. Occasionally we have to know something about hardware engineering, and I'm terrible at hardware. Like, I have actually picked up chips and I touched one to my nose and fried it completely, so I'm really bad at hardware, but we have to know at least what hardware can do and what it can't do. And then beyond that, you just keep going down this long list where we have this ... user interface, human factors and security, policy, all of these things. It just goes on and on. So there are a lot of pieces to actually making this work. Okay, so what this course is, and what this course is not, is it is not a course in theoretical crypto. So Abhishek Jain teaches a fantastic course that introduces crypto from the theory side. And I would urge you all to take it. And if you take it instead of this class, that's fine with me, in the sense that Abhishek is going to give you a really thorough grounding from which you can build. What Abhishek will teach you, he will start by teaching you about some probability and some one-way functions, and eventually, maybe you'll work your way up to pseudo-random functions, and maybe for like one day at the end, he'll talk about RSA. We are not going to do that. Instead, we're going to talk about crypto in the sense that we actually use it and apply it. We are going to start with cryptographic schemes and build from the actual use of cryptographic schemes. What I would really like to do with Abhishek is swap the order of our classes so we're not both teaching in the fall. That would be my perfect world, and then you don't have to choose between these. But I would urge you, even if whether you take this class or not, to take his class, because these things, although they're very different, are important and they relate to each other, and you should not have to choose, unfortunately, between them. But right now, maybe you do. Okay, what this class is it's a practice-oriented tutorial. We're going to examine how systems fail, how we can design cryptographic algorithms and systems that are not going to fail, and we're also going to learn kind of what the limits of this field are. We're going to learn the things that you'd love to do with crypto. How many of you have ever seen a TV show where somebody says, I got this file, or better yet, I got this piece of software, but it's encrypted, or whatever, and then they're running the program. And you're like, what the hell are you doing? If it's encrypted, how are you running this program? Like, this doesn't make any sense to me. The problem is that because of this kind of, unfortunately, there's this wishful thinking among technical experts that you can do things like that. But it's very, very hard for us to do that. Unfortunately, in the real world, there are limitations to what crypto can do. Crypto is fantastic if your goal is to say, I trust something, and I want to extend that trust to other locations, maybe across a network to other parts of the system. Crypto is fantastic about that, about doing that. Crypto cannot necessarily give you that encrypted program that you can also run. Although some more modern research, some very new research that Abhishek is working on, does actually try to do that. So we're trying to go in that way. Maybe someday we will be able to do more. But for now we have limits, and so we want to know what those limits are if you're going to actually do practical stuff. Okay, another thing that I want to mention about this class that's extremely important is that this course is driven to a large extent by current events. Okay, so things are going to happen throughout the course of this semester that are going to be interesting to us because there are security events, there are going to be crypto events, someone's going to break something really important, or there's going to be some kind of attack that's really important. And we care about those. So a lot of this course is going to be driven by you guys bringing that stuff in. And we're actually going to devote the first few minutes of every class, except for today, to talking about news. And what that means, there's another slide specifically about this, is that part of your grade, your participation grade, is going to depend on you actually going out and reading the news. And by the news, I mean news that relates specifically to crypto and information security, of which there is a lot. Now, I'll talk about some sources for this. Twitter is a great one, but you have to curate the people you follow a little bit. There are a lot of very good information security people on Twitter. But also there are websites like Ars Technica. If you read Hacker News, for example, which is great. All of these different sites, you will find interesting stuff. And I expect you to bring that in, and it's going to be useful. And oftentimes it drives what we talk about in class. But we're not going to do that today. Okay, so things you'll come away with. Again, what I hope, and I want to talk a little bit about how the class has changed this year from previous years in just 1 second. What you're going to come away from in this class is a grounding in the cryptographic techniques you need to know. So specifically, you should come out of this class knowing if I want to encrypt something or if I want to hash a password, what algorithm is the right algorithm to use for that, and what algorithm is the wrong algorithm to use for that. So if I find you guys hashing stuff with MD5, and you go off and you get jobs, which a surprising number of people who've been in this class have done, and I find that you went off to like LinkedIn and you hashed everybody's passwords with MD5, unsalted or something like that, I'm going to be personally offended by that, so I don't want that to happen. And once every now and then I have a student who goes off to classified work, actual classified work, and comes back to me and says, is it okay that we're using, RC4 to encrypt this thing? And I'm like, no, what have I done? And this is like the US, bad things. Okay, so don't do those things. You will learn not to do those. You're going to learn the strengths and weaknesses and the things you can do in crypto. You're going to learn, something about what it means to formally evaluate a cryptographic algorithm. And what I really mean about that is actually two things. One is, how do we design secure protocols and secure algorithms? We'll talk about that a little bit, just a touch of what provable security means. But the other side of this is you're going to learn, unfortunately, a little bit about what it means to validate a cryptographic module, which means something like FIPS. What does it mean when the US government says your crypto is okay? It's boring, it's unpleasant, but we're going to talk about that a little bit. So we're going to talk about standards like FIPS. And hopefully, even if you don't learn all the details of this field, you'll learn enough that you know where to start looking for more, or reading papers, or looking out on a pretty well healthy, growing field of applied crypto, which is kind of growing out in the world now. Okay. Last thing is, we want to learn a knowledge of our own limitations. So one of the things that is both scary and good is that maybe you go out and you get a job and you start building systems. And somebody tells you, we need a custom cryptographic algorithm, and maybe the answer you give is no, we want to use something that already exists. And if you do that, you've probably provided more value to the company you're working for than like anything else you could do, but maybe not. So you have to know where your limitations are and where you need to use things that already exist. Okay, a little bit of housekeeping kind of stuff that I want to get out of the way before we talk about anything really substantial. First of all, the grading policy in this class looks like so: 40% exams, 40% assignments. I'm not even sure this adds up. Yes, it does. Okay, good. 15% is going to be a course project. The course project, we're not going to get into details about what it is today, but I have a list. I have a list that I'm going to provide you. We're going to wait about a month. I'm going to put up this list, and you guys will probably form up into teams of 2, maybe 3. We'll have to see how many people we have in the actual class. And that will account for 15% of your grade. What I'm hoping by the end of the course you have produced is a piece of software, or a really good white paper, or a amazingly good presentation. I know that there is an inclination for people to like say, hey, we're going to spend 15% of our grade, and the result is going to be like a 10-minute presentation. But it really needs to be better than that. Many of these projects are try to do something new. And to give you some examples, I have a couple out here that I'm questioning now because I don't want you to get arrested. But I have a couple of projects that involve ransomware, and actually sort of seeing like what ransomware could do if people followed different directions in kind of improving it. I'm not trying to deploy ransomware, but I'm trying to see whether certain things are possible and whether we should start thinking about how to defend against them. So that's the kind of thing that I'm talking about. And so some of these projects will be on the list. You are not required to pick one off the list. If you have a great idea and you can convince me it's a great idea, fine, we'll talk about it. And the last thing that is actually very important is that 5% of your grade is going to be class participation. And the reason that's important is that comes partly from this news stuff you do. It comes from answering my questions in class. It comes from kind of being present and not just like lost in your computers, which I know happens and is very tempting. This 5% may not seem like a lot, but for somebody who's worked really hard in this class, it can be the difference between like an A and a B, or an A minus and a B, or something like that. So it's not an insubstantial chunk of the class. Okay, other housekeeping stuff. There are 2 assigned textbooks to this class. Now, I am worried that I may have actually given you the wrong one. There are actually 3, but there are 2 of them that are free and available online. And so I am going to assign pieces in all of them, so you really have 1 textbook that you will actually need to buy. I'm sorry about that, but it's a really good book to have. I'm just worried that I didn't put them all up on the website, so I have to fix that. One is a book by Captain Liddell. It's called Modern Cryptography. It's really a textbook. It's a really good book. You should buy it.
You're good?
I think so. I'm sorry to drag you out here.
Not a problem. We were in the neighborhood.
I appreciate it.
Very welcome.
The second is online and free, although you could buy it. It's a really good book to have. It's actually a fun book to read because it has lots of stories of like Ross Anderson's time, designing ATMs in Europe. It's called Security Engineering, and so the online version is completely free. There's a couple of versions online, and just the chapter numbers are slightly different. So just when I assign you something from this book, just make sure you're checking that it's the right chapter, and if you're reading one of these things. And then the third book, which is really kind of a reference, and I think I did put it on the website as a reference, but I got to check. Where's chalk? Here we go. Okay. So the third book is chalk, really? Is a book called The Handbook of Applied Cryptography. And it's also available online. It's by, Van Oorschot people, but there's only one of them, so just Google that title, and you're going to find it. It exists in print, but it's fully available online, and it's actually the same version that's in print. This is really a reference. That's the reason I included it. It's not a textbook. It's kind of like, hey, if I need an algorithm to compute the extended Euclidean, I need a pseudocode for an extended Euclidean algorithm, the Handbook of Applied Crypto will have it somewhere in the index, and you just go and find it. So that's why it's useful. Okay, there's a website, obviously. Sadly, this website is located at our old class number, which was a 650 class number. I just don't have the energy to move it because there's a lot of links that point to it and it'll all break. But if you just type into Google Practical Cryptographic Systems, even without the quote, you'll get to the website of this class. And the really important thing there is there's a syllabus on the second page, which is actually on a GitHub wiki, so I can change it easily. But anyway, it's a mess. The IT for this class is slightly messy, so we'll try to make our way as it goes. Okay, I think this just repeats most of what I said, but let me just go quickly. Again, website, slides. I'm going to put my slides up. I will try to get them up within a day or 2 of the class, maybe even the same day if I'm feeling really particularly productive. Those will go up. There's a reading assignment for today, for next Wednesday, obviously, which is going to be Ross Anderson. I believe it's chapter 5.7. It is the chapter on symmetric cryptography. So you got about a week to read that. Reading is important in this class. Reading is important. There will be things on the tests that are only going to be in the readings, and if you start skipping them, you'll be really sad. My office hours. Currently, I'm planning to have office hours on Wednesdays, obviously starting next Wednesday. I'm putting them a little bit after this class ends, just because sometimes I need to get lunch, but 2:30 to 3:30 for now. If it turns out there's a lot of demand for office hours, obviously I'll add days and I'll increase these. Last year, I didn't have very many people coming, which was great, but also made me kind of be unreliable about actually keeping the office hours. You can always email me if you really, really need a meeting and it's not possible to wait until Wednesday. My TAs. We are in the course of hiring CAs. We have a head TA. His name is Alicia Chador. He's not back. He's actually away for the summer, but he'll be back like tomorrow. So I'll introduce him during the next class. And the CAs, unfortunately, they don't have office hours yet. So we'll try to get this figured out and we'll arrange some office hours. And I'll tell you about them either by email or next time. The last thing I should say that's important is that assignment 1 will be coming out today and is due in about 2 weeks from today, I think September 13th. So it will be available, and I guess I didn't include this in our electronic stuff, on the Blackboard site for this course. So that is how I will distribute assignments. You can go there. I think I put it on a timer. It'll pop up. It will be due in 2 weeks. It's a programming assignment, and we're going to talk about that in a minute. Okay. This is a programming class. A lot of the assignments are programming classes. They involve writing code. I know in the past we've had some folks, because this is an interdisciplinary class, who are not really that comfortable with it. You know, one of the prereqs for this class is data structures. I was sort of forced to add that. It's not because I care about data structures, although data structures are great. It's because you really have to have some programming experience in order to have that prereq. If you don't have that prereq and you're really a good coder, that's still okay with me. Now, I made what I consider to be a controversial decision this year. And that decision is I'm going to force you to learn, some of you at least, to learn a new language. And the language is Go. Go drives me a little nuts. But the reason that I chose Go is because Go is one of the best compromises for building cryptographic security systems for 3 reasons. First of all, it's a compiled language, so it's fast. I've had this class done in Python in the past. Python was fine, but it's not really good if you're trying to do high-performance crypto stuff. Secondly, Go is a safe language. It's relatively hard to have like memory corruption vulnerabilities in it, so it's a good language to use. And third of all, it's not Java, which is also, I think, a plus. I think there was actually a fourth too, but I'm not sure what it is. So I'm going to make you learn Go. And one of the things you'll get out of this class is that, you know, if nothing else, you'll learn Go. It's not that bad of a language. Yes?
What's your feeling on Rust in terms of like the safe sort of new generation of young languages?
My feeling is I tried to learn Rust this summer and I gave up, so that's what I'm doing. So Rust is, I hear great things about Rust. Rust is a safe language as well, but it's just too much. I could not subject you to that. I think Go is really the threshold. Go is very C-like and very Java-like. It has a few little details, like it adds pointers, and it needlessly changes some of the syntax. But once you get used to that stuff, you'll really be fine with Go. And there are tutorials online, and there is a sandbox. Look for the Go sandbox, where you can do the tutorials without even installing it on your system, and just learn how to do like Hello World and like whatever 5 other things you need to do. Okay. Other things that you need to know. You will have to submit assignments that work. And by assignments that work, that means they have to compile on our systems. Okay, so that means we're going to specify, we'll get you details, but Go is a pretty standardized language, so I'm not looking for this to be painful. I don't think you're going to have to worry about like Python, where we have like 3 different versions of Python people stuff to work on. With Go, if you're using a recent version of Go, you'll be fine. But our systems are basically the CS systems, which are masters and UGrad, and I will talk to the TAs for people who are really, really uncomfortable, can't use those systems. Maybe we'll make a VM for you guys if you really need to do stuff on a standard environment. So you have to submit stuff that compiles and runs. Anything that doesn't compile and run, except for extraordinary reasons, once we get the bugs worked out, will actually potentially be a failure, or at least a very big chunk off your grade. Like, we can't debug stuff or take half-written assignments. That's not good. And if you say it doesn't work, maybe we can work something out. But this is really important. Okay. The course guidelines that I want to cover in this class right now. Obviously, I've already told you this 3 times, but read the news, Twitter / Hacker News, Ars Technica, etc. Bring up all these recent things that you hear about, even if they're just orthogonal, a little bit, not orthogonal, but a little off the beaten track, or they're not quite crypto. And anything that you think is interesting that you want to talk more about in class. Things that you should not do. I hope that I don't need to say this, but for some reason I always need to say this. Don't cheat. Don't cheat. I don't know why I do need to say this, but the Honor Code of Hopkins is very specific about this. If you do a number of things, and those things, I'm not going to enumerate them all, but they include working together on an assignment when you are told to do it individually. They include taking code off of the internet without saying you took code, or when you're told not to take code off the internet. They include all sorts of stupid stuff. And most of the times when I have cheating problems is I have two people who are given, let's say, an individual exam or an individual assignment, and they turn in answers that are weirdly identical. So this is the thing that happens. I can tell you the reason that I usually know it happens is because the answers are wrong. And they're wrong in like some very specific way. I had somebody tell me that 2 to the 17 was not what 2 to the 17 is. Two different people told me that. And I had a strong suspicion that since their other examples were otherwise identical, their answers, that was a pretty good hint that they had been collaborating when they weren't supposed to be. I know this can be tricky on assignments. I know people do talk a little bit about things. I'm not worried about that so much if there's a little bit of talking. But for anything that's like a test or whatever, I really need you guys not to like, you know, we'll talk about it. We'll try to work out what's reasonable, but don't do that kind of stuff. The other thing that I need to mention, and I can't believe I need to mention this, but I do need to mention this, is that I am not going to jail for you guys. So I will rat you out. I have no problem doing that. And I can give you a specific example. So a couple of years back, somebody from Johns Hopkins IT contacted me at 7 a.m. in panic, saying somebody is hammering the heck out of our Hopkins servers, and like the Hopkins directory has just gone down. And we traced it to a computer running in one of the undergrad computer labs, which had your name on the code. I was like, oh crap. It said assignment 1, practical cryptographic system. And it turned out that what this person had done is they'd done their assignment 1, which involved hitting a website or something, and then they'd taken out all the actual code for the assignment, cloned the file, and then stuck in something that tried to like scrape a whole bunch of stuff off the Hopkins servers, but they did it in such a way that it was just like completely killing the crappy Hopkins infrastructure, which is crappy, admittedly, and should have been able to handle it. And it ended up with me being woken up, and I don't like that. So I do not want you to do this, and I'm somewhat joking. I'm only somewhat joking. There are things you guys might be tempted to do. I'm going to tell one other fish story. It's not a fish story, it's a real story. I advised a couple of guys at University of Maryland a few years ago, and they were looking at EasyPass, which is the toll collection system. By the time I had arrived there, they had figured out a couple of really interesting things. One of which was that if you looked on the Wayback Machine at the transportation, the EasyPass website, the current version had a username and password on a protected area of the site. The old version on the Wayback Machine also had a username and a password, but the password check was implemented in JavaScript on the client side, and the password was in that code. So they had taken that password, and then they had logged into the current version of the site, and they had downloaded a whole bunch of not publicly available documentation on how EasyPass works. That stuff actually is potentially, if a prosecutor is motivated, is actually a federal crime. It's a violation of the Computer Fraud and Abuse Act, and prosecutors have a lot of power to do bad things to you, even if it seems very innocent to you in terms of technically what you did. By the time I got there, they had already hatched a plan to buy hard hats and drive to a toll collection subsystem that happened to be located by the side of a highway a little further south in Maryland, and we're actually going to open up the doors and look inside and see how everything was wired together. So I talked to them at that point, and I got them a lawyer, and then they dropped the whole idea because they were so scared about what could happen to them. Okay, so don't do these things that are bad and can get you in trouble. And the last story I'm going to tell you on this subject, hopefully to scare you just a little bit. Does anyone know the name Malware Tech Blog?
Yeah.
Okay.
I was going to bring him up.
So this is a researcher who went to DEF CON this summer, and he was actually pretty famous right before this because he had created a sinkhole that happened to kill the WannaCry worm, which is really good. Everyone loved him. He was great. He went to DEF CON. He went, spent a week driving around doing fun stuff in Vegas, and then he was arrested at the airport on his way out. And so now he's not in jail. I think he's out on bail or whatever. And the allegation is he did something really bad, which is that he sold some code for a piece of malware to some folks who were using it as a banking Trojan. So this is not some guy being arrested, at least for doing his research. my point is that if you're working on stuff, particularly stuff that is on the edge of research, like looking at ransomware, there is room for misinterpretation. Now, I don't know if he did something that was research-wise that just went over a line, or if he actually did the bad stuff he's accused of. The point is, you don't want a prosecutor making that decision, so just talk to me before you do interesting research projects. Okay. Okay, readings. I've already assigned you one reading assignment. I'll put that up, but the readings are assigned each week. You have to read them. They're due the next class, typically, or sometimes like 2 classes. And so I'll try to tell you what these will be. These are going to be covered in written assignments on homework, etc. So you've got to be able to read these and talk about these in class. Okay, last incidental thing, hopefully the last incidental thing, is there's a Piazza page. I just activated it last night. You just pretty much have to just go to piazza.com, type in Johns Hopkins Practical Cryptographic Systems. It will pop up. That's it. You guys can post on it. You can post anonymously, whatever. You can do whatever you want. And please use this as a resource to talk to TAs. Use it as a resource to talk amongst yourselves. Like, that's all fine. Do that. I don't have a lot of travel scheduled that will disrupt this class, but occasionally I do have to travel places. I will do my absolute best to get a good substitute if that happens. But I'm going to assign reading, even if you guys have a substitute doing stuff. All right? So that's that. I think that's actually all. I have this sneaking feeling that I have something else important to tell you. Oh, yes, I do have something else important to tell you before I get here. Okay, in the past, this course has had a slightly different structure. So when I created this course, the goal was to assume that you knew crypto. It just happened that the way the course was laid out, we had a crypto class in the previous semester, and then this was, okay, you've learned some crypto, let's go ahead and build systems with it. Because that's not really so true for all of you, I've just given up on that idea. In this class, we're going to spend a bit more time kind of covering fundamentals of algorithms than we have in the past. So that's one big difference. The second difference is that because we're trying to cover some of these fundamentals, we're going to be doing some more low-level kind of coding assignments. Whereas in past classes, we typically have like 1 or 2 or 3 big assignments. Here we're going to have 3 big assignments. Here we're going to have maybe more like 5, depending on how things go and whether we have to delay things. Maybe 6, but probably 5 assignments. And they're going to be things like implementing algorithms from scratch and so on. And you're going to do it in Go. So that's going to be another difference. All right. So things have changed. If you have, let's say, stories from people last year or the year before or whatever, take them with a grain of salt because they may not be true anymore. Okay, good. So I'm going to spend the rest of today, depending on how we do for time, I'm going to spend the rest of today kind of giving an introduction of how crypto really affects you and what exactly this class is going to be about. This is a very high-level introduction. Before I go on with that, though, I'll give you guys a chance to ask any questions that about the structure of this class that you might have after that long thing. Yes?
Are exam dates set in yet?
I think I put some exams on the syllabus. The midterm, I think, is like right in the middle of, I don't know. It's on the syllabus. You can check it out. There is a midterm exam scheduled in class. I've been getting a lot of crap from the Hopkins administration. In fact, everybody has been getting a lot of crap about when to schedule finals. The Hopkins administration really, really hates it when we do them in class. They are putting up with it, but they're getting really, really annoyed with it, and they really want us to do it during the final period. So as I hate it, everybody tends to hate it, but then again, some people like it because they get reading periods to study. So as we get closer towards the final, I guess we'll make a decision about how we're going to do that. We'll sort of punt on that for now. Any other questions? Yes.
Do you have to be actually enrolled in the class to access the Blackboard?
I don't think so. You should be able to access it. If you find that you can't access it, it's no problem. Just send me, or ideally send the TA, whose email I'm going to give you. Actually, whose email I'm going to put up, because I don't know which email he wants to use. I'm going to put it up on the Piazza page. But send the TA a note, and he will add you as like a guest or something, and it'll be covered. Anyone? Yes?
So I'm already enrolled in the class, but I didn't see a Blackboard class.
Oh, God.
Me neither.
Weird. Okay, it could be, I thought I had activated the Blackboard site, but there's like some weird little option hidden in the submenu. Does anyone have a pen on them? I'm going to. This is not a pen.
Pencil?
I need it because I'm
There you
gonna
go.
write on my hand and the pencil.
Oh,
I'm not
okay.
gonna do
Oh,
it.
okay.
Here you go.
We'll just push harder.
Activate Blackboard. Okay, there we go. All right.
Got it ready.
Okay, good.
Yep.
Any other questions? Yes.
So you're saying you're using Piazza as well, like, would we be able to just use Piazza or just use GitHub or just use your class website? Is there one place we could go for everything?
Yeah, so I hate Dropbox, but the grading features, as much as I hate it, are better than anything else that's privately offered. But Dropbox sucks for discussion and for everything else. That's why I'm splitting.
Hasn't Dropbox also been in the news for all sorts of horrible mismanagement of privacy and
Yeah,
cryptography
Dropbox
issues?
is a nightmare. It's like an HTML 1.0 application that somebody threw together and sold for like zillions of dollars. It's terrible. It's the worst thing in the world. However, it integrates tightly with Johns Hopkins grading infrastructure, and so it's worth it to me to use this crappy application. I've actually written like angry blog posts about Dropbox and then deleted them because I was like worried that I was going to get in trouble. So Dropbox really pisses me off, but we are going to use it just for submitting and getting and downloading assignments, and that's all. If you are not enrolled in this class and you can't get into Dropbox, we'll make you enrolled. We'll figure it out. Don't worry about it. If you're not even a Hopkins student or something, we'll figure it out. I don't care. Okay, good. All right. So today we're going to talk a little bit about how these cryptographic systems work and how they fail. Okay, so one of the things that I like to tell people about, if you haven't been in this field, there are actually a lot of different groups in information security, but I kind of consider there to be kind of three groups that I encounter on a daily basis. And one of them is kind of academic cryptographers. And academic cryptographers are important because for the most part, these are the people who are actually designing cryptographic algorithms and to some extent cryptographic protocols, although the IETF also does that, so there's a little bit of an exception. Maybe they fall in the second class. The second big group, which is hugely generalized, is people who, are security folks. Maybe they're academic security folks, maybe they're just people who kind of study security, but they're not academically trained. It doesn't matter. There are a lot of these people, and they do their own thing, and there's some overlap, of course, with the crypto people. But finally, there's this third group, and these groups are kind of the folks who actually build the majority of the stuff we use. So when you buy, I don't know, this crappy projector setup that Hopkins got, if it has some security in it, or if you buy an embedded device that you're going to plug into your home, the chances are that the people who actually designed that and implemented that are not really trained in security. They don't even work in security the majority of the time. They're just a different group of people, and they've maybe gone online or they've read some books and they think they know how to do stuff, and the result is usually stuff like this, simple unbreakable encryption, like clearly kind of crappy products, and there are a lot of crappy products out there. Now, there are some exceptions to this. There are a small number of people in the world who really know their stuff. This is Moxie Marlinspike. That is not actually his birth name, but he's Moxie Marlinspike. What did Moxie Marlinspike do for you folks? Anyone know him? What is he famous for? Or apparently not very famous for in this class?
I've heard the name.
Isn't it like Open Whisper or something?
Yes, and what do they do?
I think they make like cryptographic software.
Yes.
Open source.
So Moxie Marlinspike created an app called Signal. And Signal, you may or may not have heard of. Maybe you have. It's been in the news a bit lately with the elections. But it turns out that the Signal protocol and his libraries are now used in WhatsApp. They're used by Facebook Messenger. They're used by Google Allo. So anything, any text, phone app or texting app that uses end-to-end encryption is probably, with overwhelming probability, running some of Moxie's code in it. So he's a person who really does know what he's doing. But there's, there are people who don't. Okay. So what does this mean to us? Well, what happens when security systems fail? Generally speaking, that's really good for us. Researchers who find flaws in security systems do well. We get to publish. You get to give talks at Black Hat and DEF CON, and that's fun. That's great. But oftentimes, a lot of money gets lost. And that the ironic thing is that in most cases, this is not money being stolen. This is money just being lost. So for example, this recent couple of ransomware attacks that came out, one of them was WannaCry, and there was another one right after it. Maersk, I think that's how you pronounce them, they're the shipping provider, the pretty famous shipping provider. They claim to have lost something on the order of $200 to $300 million just from one ransomware attack, because all of their systems went down. Now, the people who made, let's just say WannaCry, does anyone know how much money they actually got away with at the end of this?
30,000.
I think it was about 100,000, but that's only because the price of like Bitcoin went up or something during the course of this. So ironically, the criminals who are actually breaking systems in real life, it's not a very profitable industry the majority of the time, unless you're stealing people's Bitcoin. But the rest of the time, it really, really costs industry a ton of money. Of course, you know, there are times when it's not so much money being lost, but it's usually your stuff being lost. It's private information, your passwords, and so on. Is there, does anyone know a good place to see if your passwords or your credentials have been compromised? Yeah.
Have I been pwned?
Have I been pwned? So yes, so Troy Hunt runs, it's Troy Hunt, right? He runs a website that basically just aggregates all of the data breaches that have happened recently in major websites. You can look up your credentials and so on. He's a good guy. I think he crossed 1 billion records, or maybe he crossed, you know, more than 1 billion records. I'm not quite sure, but there's a huge amount of data. It's actually gotten to the point where he's having database scaling problems. There are so many records in his system that he writes blog posts about how hard it is to handle this much data. You may think this last one is being hyperbolic, that people could die as a result of a security failure. Of course, not totally true. Anyone here ever read The Cuckoo's Egg? Cuckoo's Egg is a book written by Clifford Stoll. It takes place back in the 80s. It was written back in the 80s. And it's about an East German hacker who broke into a bunch of systems on the very early internet. Well, one of the things that East German hacker did is he hacked into a computer called the PET-VAX, which sounds really cute, right? The PET-VAX, it's someone's pet VAX. Except that PET stood for positron emission tomography, which was actually the computer that was driving a beam of positrons that was going into people's heads as they were getting, you know, treatment. So anything this guy had done, up to and including maybe just overload that computer, could have really hurt someone. So these kind of things are real. Now that's a long time ago. What happened recently? Anyone hear any news recently about things that might have affected people's life or health? Yes.
Well, I mean, there was WannaCry and health systems going down and medical records not being available.
Tons of medical systems, not just medical record systems, but the pacemaker. Yeah, okay, good. Hold that one for a second. MRI systems tend to use Windows, old versions of Windows. Those go down. Yeah.
Hacking into motor vehicles.
Oh yeah. Okay. Couple of guys. You know the names of those guys?
I used to.
So Charlie Miller and Chris Valasek, they've been basically going around hacking cars, and they got to the point where they could hack a Jeep remotely just by knowing its phone number, and they could send a command to it that would basically shut off its brakes or trigger its accelerator or do anything they wanted. So these things can happen. Mostly not killing people. All this ransomware stuff really could hurt people and probably has hurt people. It's cost $300 billion to Maersk, and it's doing the same thing to hospitals. Probably somebody has been adversely affected by this. Somebody mentioned pacemakers. There was a recent sort of long-rolling but very under-the-radar bit of news about a company last September who found bugs in St. Jude Medical's implantable cardiac devices. And these are devices that basically give your heart large shocks to get it going again when you go into, what's the word here?
Arrhythmia.
Yes, when you have arrhythmia. And these devices, it turns out, they take commands over a radio connection that can be distance of hundreds of feet. There was no authentication on the communication protocol that these devices used. If you figured out a hard-coded 3-byte password, which was present in a lot of their software, you could send a command that would kill somebody and they would die. And I saw people do this, fortunately not to actual humans, but just to the devices on a table with some electrical multimeters plugged in. So people could die. And the really scary thing is these attacks, you know, if they're combined with something like ransomware, could actually be very practical. Yeah.
I think a similar issue is the sort of limitless, boundless, and almost proliferation of the Internet of Things, where people seem to think we can put the Internet everywhere. And I actually think it's bad that I don't think it's good that cars are starting to run Android, especially considering they're using Linux 3 for their kernel.
So a lot of things that should not be plugged into the internet are being plugged into the internet, and they're increasingly doing important stuff.
How do we stop people from doing that, Ted?
You don't. It's too late. I mean, people are plugging everything into the internet. You heard about Stuxnet, which was a industrial controller system that had been hacked. Well, modern industrial controller systems now have Windows built into the actual PLC controller, and they are connected to networks, so it's just going to get worse. Hopefully security will get better to make that kind of thing safe. But right now we're in a kind of a weird and dangerous period where like nothing terrible has happened yet, but it might happen, and we'll see. And it'll be interesting. Maybe it'll happen this semester, and you guys can bring it in and tell me about it. Okay, so when we talk about the different pieces of crypto, or at least of practical cryptographic systems, I'm going to break it up into 5 basic categories. I'm going to start very high level. One of the things that we care a lot about is concept. So I'll come back to this and show you. Oh, sorry, for some reason I'm not even going to get to concept. Maybe that's later. I'm going to start with primitives. Okay, so one of the things when you talk about crypto or cryptographic systems, one of the things people think about is they think about primitives. Primitives really refers to algorithms. We call them primitives because that's just a thing that cryptographers do. These refer to the codes, the ciphers, the encryption schemes, the message authentication codes, and so on that we use at a low level. Unfortunately, a lot of people who take crypto classes never really get beyond primitives. You learn a lot about these algorithms, you think you know everything about crypto, you go out to build a system and bad stuff happens. But if we go back in time, and by classically, I mean classically like hundreds of years ago, there were no computers. So when you talked about attacking cryptography, you were talking about an attack on a primitive. You were talking about cryptanalyzing a specific algorithm. And the interesting thing about this is that history is littered with these broken primitives. Now I've put up 3 examples. I'm sure one of them is very recognizable. Can you tell me what some of the others are? Anyone? Yes.
The Enigma.
Good. The left side is the Enigma. As we know, this was very famously broken due to usage problems on the part of the Axis powers. And the Enigma actually changed the course of World War II. This is one of the most famous examples. What about the other 2? So this one I will give you. It's a fairly simple substitution cipher. You wouldn't recognize it specifically, but I'll come back to that in a second. So substitution cipher is very, very, very popular if you look at the history of crypto. These things have been broken for probably thousands of years now, but people just kept on using them. So very obviously broken primitive.
Is that a block cipher?
It is not a block cipher, it's a stream cipher, and I expect you probably can't see it very well, but if I told you that these 2 boxes said I and J, and this says SI, SJ, SI plus SJ. Anyone? Just curious if you recognize that.
Electronic code book.
What's that?
ECB.
No, it's not. This is the RC4 cipher. The RC4 cipher, some people say it stands for, officially it's Revest Cipher 4. Unofficially it's Ron's code 4. Revest Cipher 4 is probably the simplest modern cipher you can download. It's about 5 lines of C code. You can even get it off of the Wikipedia article. It is unfortunately very broken and has been used in a lot of systems recently, meaning the last 10, 15 years, including WEP. WEP was entirely based on this cipher. It was used wrong, and the result is that if you have an old device that supports WEP for wireless, it's totally busted. But it's also used in the internet for TLS, and it's busted there too. So these things get broken, and bad stuff happens. Okay, so let's talk about some other examples of primitives. I'll tell you a story. So once upon a time, the people who invented GSM encryption, which is to say the European telecom standardization industry, or whatever the name is, these folks decided that old-fashioned analog phones, which they were replacing, were a huge security nightmare. And why were analog phones a security nightmare? This should be an easy question. Does anyone remember analog cell phones? This is before your time, I admit. But you understand that before digital cell phones, there were analog cell phones. And so thinking about this in sort of an intuitive way, why would analog cell phones have been a security nightmare?
Because they were pretty trivial to intercept and be able to capture.
These things were basically CB radios in a nice package. They were not encrypted, they were not protected in any way, and there were a bunch of examples where, and this tells you what it takes to change the law and change standards, where people went around with CB radio antennas, and they recorded politicians talking about confidential things on their analog cell phones, and then they put them on the radio. After which, all of a sudden, encrypting those cell phone conversations became a very high-level priority for many different politicians, as you can imagine. So when the folks who invented GSM encryption, how many people here know what GSM encryption is? Or GSM, sorry, not GSM encryption. Okay, how many people here have a cell phone that works in Europe? Okay, so if you have a modern cell phone, whether it's an LTE, which is long-term evolution, or if it's a really kind of any phone, the only exception would be like a Verizon phone, which uses CDMA. All of these phones are based on something called Global System for Mobile, which was a European digital cellular phone standard, which came about in the early 1980s maybe. and was standardized and has eventually kind of taken over, with a few exceptions in Asia and the United States, has taken over as the global standard. If you can roam from here to Europe or to Mexico or wherever, the reason is because you're using either a GSM phone or a GSM-derived phone. So if we go back to the 80s and 90s, when the first versions of GSM were invented, the folks who were designing it were told, add encryption, at least from the phone handset to the cell phone tower, so we can get rid of these folks who are recording stuff. And so they came up with a bunch of different algorithms, and these are just kind of flags you can turn on in the protocol. Okay, algorithm 1 is called A5/0. It's no encryption, so not really an algorithm at all. It's just the identity function here, so we'll leave that alone. They came up with one called A5/1. This is an actual encryption algorithm. It's actually a stream cipher. I'll talk about what that means later. It's based on linear feedback shift registers, and actually this is it. A linear feedback shift register is just, if you haven't seen these before, these are just registers where you have a few XOR gates and the ability to push all the bits in this register in one direction, I guess left. And so what happens is a few bits come out, go into these XOR gates. A new bit is calculated as the result of that and gets popped into the right side of the register. And then all the bits get shifted left, and one bit pops out of the left side of the register and goes off to be used. Okay, so linear feedback shift registers are not very secure to build ciphers with. The idea is that you could somehow build just a simple linear feedback shift register, pop the bits off, and maybe XOR them with your message, and that would be enough to build a secure cipher. Well, that's not true. These things are not secure ciphers. So the people who built A5/1 decided that they couldn't just use one linear feedback shift register. They would use 3 with slightly different functions in it. And then they would take the outputs of all those things and they would XOR them together, and that would be a secure cipher. Okay, so this was their design thought. Now, if you look at this, this has to be the world's simplest encryption algorithm. If it's 1985 and you're designing an encryption algorithm, why would you pick this particular design? What's appealing about it? Yeah?
It can completely be done in hardware?
Completely be done in hardware, and it's cheap. I mean, remember, nowadays we can use all kinds of complicated crypto. Back in 1985, this would have cost actual money, even this little dumb circuit. So they were trying to minimize the amount of money people would have to spend on these handsets. So that's one reason. The other reason, which Ross Anderson talks about in the book, is there was actually a big tension between the folks who were on the border of the Warsaw Pact, meaning the USSR-affiliated countries, and the folks like France and Germany. And the tension there was that France and Germany, their law enforcement wanted to be able to eavesdrop and break this encryption. The folks who lived next to the USSR, they didn't want people to be able to break their encryption. But France and Germany won. And so this was not just a cheap algorithm, but it was actually known to be kind of a bad one. And the secret services of those countries liked that feature. But if that wasn't enough, this organization came up with an algorithm called A5/2. This is literally A5/1, where you lop off like most of the bits of the key and just use a very small, like truncated version of the key. So it's weak. And it was designed to be weak. It was designed so that the Europeans could export it to all of these other countries who were also installing cell phones at the time, and then they could sit offshore with ships with big antennas on them, and they could very easily spy on those countries. And I'm not joking. This is actually why they designed A5/2. It was export only. Nowadays, there's an A5/3, which is used in 3G and so on, so it's a better algorithm. But a lot of people here in the US and elsewhere still use these A5/1 and A5/2. Okay, the very, very long conclusion to this kind of lecture is that A5/1 is pretty much completely broken. But not as broken as A5/2, in the sense that A5/2 I could break on my laptop. A5/1, I have to download a big file, and then I can break it on my laptop. It takes like 30 seconds, whereas A5/2 takes like less than a second. So they're both broken, but one is really broken. This one, A5/3, is dented in the sense that we don't really know if it's secure, and it seems to be kind of failing, but it's not known to be broken. Okay, so I said there were reasons for this deliberately weak design. This is an article from 2009 about a German computer engineer who deciphered and published the algorithm for A5/1 and also talked about how you can break it. Here's an algorithm from all the way later in 2010 that talks about the attack on 3G and so on and so forth. So these things came out and these algorithms have been broken for a long time. Has anyone heard of the Stingray? Okay, so a stingray is a device that allows you to intercept people's phone calls. It doesn't break the encryption, typically. It downgrades the encryption. It'll downgrade you from A51 to A52, and then it'll break A52. So this is basically, these kind of algorithms are very practical, and people use them in real life. Yes?
Are the 4G systems also as horribly, completely, consistently broken?
Many of them still use Kasumi, so as far as I know, it's dented but not broken. But almost all of those systems, just as a detail, can be downgraded. So I can just block the availability of a 4G or an LTE tower and present you with a classical GSM phone, and the vast majority of your phones will just happily connect to that fake tower, thinking it's the only one in the area, and then I can relay from my fake tower to the real tower. So in practice, it's broken too.
So like in Canada or Mexico or Europe, would it be going through the GSM version 3?
It would really depend on the provider, but it would probably be going through the more recent versions. Yeah. You'll see, if your phone says 3G or 4G or LTE, it's running the newer version. If it doesn't say those things, you're running the old school GSM. Okay, so there are a lot of problems here. So typical problems include using the wrong primitives and writing your own, which is even worse. You could use the right ones wrong. Example I gave was the RC4 algorithm, which is used in WEP and TLS, was done wrong. And so as a result of that, it was particularly broken. We'll talk about later about what that means. Okay, another thing that happens is sometimes the right primitives, the ones that we think are secure, stop being right. The good news is that most of the time we learn about this early. So we have a chance to fix it and to upgrade to newer crypto. The bad news is that we never do. And so what happens is stuff like this. I don't have all of the history of this, but MD5 in 2000 was found to be a weak hash function. Hash functions are used in digital certificates, so they're really important. Signing codes, stuff like that, was found to be theoretically weak. Nobody did anything. In 2005, people said, no, it's really weak. We can kind of break it right now, but not totally practically. Nobody did anything. In 2007 or 2008, people actually showed that you could forge digital certificates for websites, and then people begrudgingly started upgrading to a different hash function. Some people. In 2000, and I'm forgetting the date, but I think it was 2011 or 2012, someone went to Microsoft's website and obtained a forged signature or forged certificate from their servers by actually breaking the MD5 hash function. And the interesting thing about this is the attack they used was completely unknown. It was a different version of an attack that was known on MD5, but also completely different mathematically, which indicated to everybody that this was probably an intelligence agency. So in 2011, 2012, because Microsoft didn't shut down MD5, an intelligence agency was able to get a certificate, and they used that to deploy a piece of malware called Flame. So we're talking like 12 years after MD5 was found to be broken. People like Microsoft are still using it for software signing, and as a result of that, we have malware. So these things actually do matter. Okay, I mentioned RC4 and TLS, but I'm not gonna cover that one too much right now. Okay, sometimes the right primitives also stop being right because the world changes around us. I'm going to talk more about this later in class, but one of the big scary things that's coming to crypto is quantum computing. And everybody's in a panic because we think these computers may be 10, 15 years away, and they will break every public key algorithm that we currently use. All public key crypto will die. And we are looking for new algorithms on different based on different mathematical properties that will be able to resist these machines. And we're very hopeful we'll be able to find them in time. So these things are happening too. Okay, so sometimes the primitives are not the problem. Primitives are what most people start with, but sometimes what actually breaks is not the primitive, it's the protocol. What is a protocol? Well, a protocol, of course, you can think of the English language definition of protocol. A protocol is just a set of rules by which you do different operations, perform different operations. A cryptographic protocol is a set of rules and conventions by which we perform cryptographic operations. If you go back to the 1500s, the classical cryptographic protocol was pretty much one flight of data. One person would encrypt a message, they would ship it over the through the forest full of barbarians, and it would arrive at its destination. And if somebody intercepted that message, well, they pretty much had to go back and break the primitive in order to decrypt it. So there was not much protocol stuff going on back in the day. Nowadays, modern systems do tons and tons of things. Every time you make a connection to your website, your computer is making 4 or more round trips to establish different options and decide what kind of crypto it's going to use, and then finally encrypting that website. Every time you use a credit card, there's a similar kind of exchange of information. And it's even worse, because in the classical world, your attacker was some guy who's in the woods who would intercept your message going through. Not very easy to do. In the modern world, oftentimes your attacker is the person who actually is running one side of this device. You know, you're a store owner who has bought a credit card machine. You might also be the person trying to hack this protocol, which means you don't just get one shot to break it. You could try it thousands and thousands of times, and maybe you get lucky on the 999th time, and so on. So you get a lot of different kind of powers in modern cryptographic protocols than you used to. Let me give you an example of how we can go from something simple to a cryptographic protocol. Okay, so there is a device that is called a vehicle immobilizer. How many of you guys actually own cars, drive cars? Okay, so it's a reasonable number. How many of you folks used to have a car, or had an old car ever, that had a simple piece of metal as the key for the car? Okay, so once upon a time, keys were just these metal things. They were physical keys. You put them in. If they fit the tumblers, they would turn the lock. And obviously, everyone's car got stolen, or a lot of cars got stolen, because that's really easy to defeat. You can buy knock keys which fit into the tumblers, you can break it open, you can connect wires together, and it was bad. And so at a certain point, insurance companies began demanding that there be some additional digital security measures inside of cars. And they invented this idea called the immobilizer system. If you have a key today, whether it's a physical key or a contactless key, it's got a chip inside of it. And that chip has a radio transceiver and talks to something usually near the stock. If you have one of the ones you have to actually plug in, near the steering wheel. And it actually sends some kind of digital message. So even if you could force the lock, the car will not start because the fuel injection system will not activate if it doesn't receive the right digital message from your key. In the olden days, in the earliest days, like 90s, when these systems were first being deployed, the message was literally just a password. It was like, I'm calling it a serial number, but whatever it was. There was a single value that was stored on your key. Every time you turn your key, the chip on your key would transmit that same password to the car. What's the problem with this?
You intercept it with like a software-defined radio and just replay it.
Good. Replay attacks. There is no crypto here. Anybody who has the right kind of radio could just record this. And in fact, there was a whole class of attacks called valet attacks, where people would build little devices that would sniff, do exactly that. You'd give your key to a valet, they would press it up against the device to copy the password, and then they would sell it to the kind of people who actually do steal cars. And so gradually car theft began to go. Car theft initially went way down in these newer cars and then started to shoot right back up because criminals, especially organized criminals, will always find a way. So this was not a great solution. But how do we fix it? The idea that the car manufacturers, I'm sorry, this is my illustration of that attack, whatever, it's a replay attack, this is called. The idea that car manufacturers came up with was to build a protocol. The protocol is called a challenge response protocol. And the idea was that instead of sending the password over the air, they would bake into the system, bake into the key, the physical key, a value, which I'll call the cryptographic key, a value K. And this was a secret value which would never leave your key fob, but a copy of it would also be installed in your car engine. And so what would happen is your car would come up with a challenge, which was basically a big random number. It would send that random number over to your key fob, and then your key fob would compute a cryptographic function F using the secret value K, but not revealing it, on that challenge value that had been sent, and it would send the result back. And the beauty of this is if this function is good, it should be two things. First of all, it should be hard to figure out the value K from seeing one challenge. That's good. Secondly, it should be hard to make up these challenges unless you know K. It should be hard to compute F on K if you don't know K. It should at least be difficult. And third of all, if you replay a captured version of this value, this response value, it's useless because the next time you try to start the car will send a different challenge. And so replay attacks are blocked. And this was a really good system. Yeah?
One question I have is, depends on, are there enough possible challenges? Like, are you limited by like
We
known large
would start with,
time?
let's say, a 40-bit challenge or an 80-bit challenge. So lots of challenges are possible. So we'll just assume a very big random number. Okay. So, I don't want to show you that. How do you break the system? How do you break the system? Anyone? Okay, maybe you can't break it. How do you steal someone's car? You have to steal someone's car. or your whole family's going to be killed. The mob tells you, figure out how to do it by tomorrow. You guys will solve this problem somehow. What are you going to do? Yes.
So I can ask the car to give me the challenge, and then I will send the challenge to the key and get the answers from the key, and then send it back.
So I will get two people, me and my buddy will follow around the person with the key with one radio transmitter, and we'll have like an internet connection between me and him. And I'll have another radio transmitter, and I'll hang out by the car. And exactly, so we'll do exactly that. The car will send a challenge, I'll intercept it, I'll send it over to the other transmitter, it'll go into the key. Notice we haven't broken the crypto of this at all, we're just kind of abusing the protocol slightly. Okay, so we can do this. This is called, in some cases, it's called a man-in-the-middle attack. It's just, we're just routing the communications. No crypto attack. We could, of course, attack the crypto. That would be even better. But let's just assume for now we can't. We're just talking about protocols. Okay, how do we stop this attack? How do we cut this down? Because this actually started happening too. It's a little, what's that?
Maybe a time limit.
Good, good. So what do you mean by a time limit?
So obviously, in order to route that key through all those other kind of nodes and transport, it takes time. So if you set a time limit based on how long it takes to compute that challenge, then you kind of have a limit.
Very good. Okay, so exactly. So if we take the light speed time it's going to take for the radio signal to reach the key and get back, plus the computation time, we can set a time limit, exactly like you said, and we use that as our round trip time upper bound. We don't get a response back in time, we just don't accept the communication. Yeah.
There could also be requiring the physical corollary. Like you could say, I need to have a key that actually fits in this thing.
You can do that, but even then, somebody can actually, break the mechanical security of that. So this is maybe an alternative to doing that, so you don't have to rely on mechanical security. So, yeah.
So even if you got in, so if you unlock the car, you won't be able to start it if you don't have the key.
So a lot of cars nowadays don't even have a physical lock anymore, because the digital key is so much more secure. It's just a button nowadays.
Yes.
So in those cars, you're fine.
Okay.
Yeah, but honestly, the physical locks were never that good, and criminals figured out how to defeat them a long time ago. Some people tried high security keys, but every single one of those just got busted. In fact, physical locks are pretty much a dead end when you compare them to digital systems at this point. Okay, so this kind of problem, this thing I'm talking about, not only happens in cars, it happens in airplanes. There is a system, I only have 2 minutes left, but I'm going to use them. There is a system called IFF, which is, what does IFF stand for? Something friend or interrogate friend or foe. Identify friend or foe. So your radar transmitter does exactly what I just described of these automotive immobilizers. It sends a challenge to an airplane, and the airplane has to send back a function of some key and that challenge to prove that it's legitimately an airplane. Well, there's a chapter in the Ross Anderson book that actually talks about how, I believe, the Israeli army was able to defeat this in an actual battle. And they did exactly what we just described. They put a receiver here, and they went and they broadcast the connection over to another plane, which would actually talk to a legitimate plane on the same side, on that army or that air force that had the right IFF, and they simply relayed them from their own fighters to make it so that they could appear as though they were the actual, I guess in this case it was the South African army, I believe. And so they were actually able to sorry, maybe it was the Cubans. I'm getting this all wrong. But the rough idea is they implemented the attack we just described. Okay? So I'm going to take 1 more minute. I'm going to talk about an example of, actually I'm not. I don't have time to talk about it. We'll pick up next time right where I left off, and we'll talk about some people who implemented the system and how it breaks. And I'll see you guys next Wednesday. That's a long time. Do your reading. Check out the course syllabus. And if you're going to drop the class, sooner is better.